engineers in the house. All right, so here we go. Part one, motivation. So to better understand why GPU computing is so interesting today, can I just stop using the mic? Can you guys hear me?
No.
Okay, all right. That's right, there's a video, it's all on tape. Okay, so yeah, so to better understand why GPU computing is such an interesting processor, we'll need to look at some technology trends. So it turns out modern day processors are actually built from transistors. So they're built from modern day processors are built from transistors. And so what this chart shows is the feature size and the over time. And what you're seeing here, the feature size is the minimum size that a transistor takes up on a chip. And what you're seeing here is as the feature size is decreasing over time. Okay? And so that's the good news, because when feature size is decreased, that means we can fit more transistors on a processor, and then they obviously run faster, they take less power to run, and we can squeeze more of them on the processor. So that's the good news. For that period of time. But it turns out we've actually run into a problem and a bottleneck for instruction level parallelism that we can achieve per clock cycle. So that is also a bottleneck. Option 3 is to just hire more diggers. And that is really the motivation for the GPU computing that we have today. The idea is instead of having more powerful processors, you have more or less powerful processors that are able to, sorry, what's that? Don't hold the bottom. Okay, thank you. I think that was it. That's going to take us over this next hump. So yeah. Wow. That was like amazing.
Or as Steve Jobs says, you're holding it wrong.
Alrighty. So now let's dig at this concept a little bit further, okay? So we need to basically figure out if we're going to be designing a processor, what are we optimizing for? So it turns out I want to introduce these two dimensions. The first dimension I want to introduce you to is latency, and that's basically the amount of time it takes to complete a task. And the other dimension is throughput, and that's the tasks you can complete per that unit of time. And so let's say you wanted to take a trip from California to Virginia. There's about 4,500 kilometers in between. If you could, in this case, you have two options. The first option is to rent a sports car that can take 2 people at 200 kilometers per hour. And then today is because researchers have invested a lot of energy into figuring out how to parallelize the training algorithms. And part 3, a company called NVIDIA has helped create CUDA, which introduced this programming model that allows us to parallelize our code. Okay. So if you're sitting there wondering, so what? This is all really cool stuff, but what's in it for me? How can I leave this room and take action on this stuff? Well, I want to give you a little, algorithm for that, okay? So where I'd like you to start off is I'd like you to first use and leverage accelerated libraries. By a show of hands, how many people here have used TensorFlow? Great. Who hasn't? Let's see. Who else? Who's used, let's say, Cafe or MXNet? Okay. How about Torch? How many people here have used Torch? Okay. Let's see you again. Okay. So all of those libraries that you've used are actually you're able to use them because it hides a lot of the GPU computation away from you through this library called cuDNN. So cuDNN really powers all of those libraries that you're using. So you don't need to get a PhD in GPU computing to use that. So where should you start? Where you currently are. You're already doing it. But if you're also looking for parallelizable algorithms, I recommend you look into Thrust. If you're familiar with what STL did, the standard template library did to C++, that's a step in the right direction. It's kind of the same idea, but for parallel algorithms. We'll take a look at a code snippet next. And then, so if you're kind of exhausted the whole accelerated libraries option, I recommend you use compiler directives. So by sprinkling your code with a couple of programming directives, you're able to, again, rely on the compiler to take care of all those details of parallel data movement and processing. Now, if you're not happy with the performance from the first 2 options, then it turns out you're going to need some low-level customization, and CUDA is the language for this. so there's a little bit of terminology. The host is the CPU. Don't push the bottom. The GPU is referred to as the device. So when you, first step is to allocate data. Next step is to copy it from the CPU to the GPU. The third step on line 21 is to do the actual work, and that work is done in parallel. And line 24 copies the data back from the GPU to the CPU. Okay? So if you want to dig a little bit more of that, CUDA 9 also obviously supports unified memory, so check that out to get the most recent modern day up-to-date information on that. But that's generally the structure. Okay, any questions so far? Cool.
Yes.
Yes, okay, great.
Where does OpenCL and Vulkan fit into this?
Yes, very good question. So NVIDIA's CUDA is proprietary. OpenCL is an open standard.
Yep.
So that should, you know, if you're, I don't know, depending on the business model that you have, if that's a limitation, then OpenCL would be the way I'd go. And it's come a long way. And so I think just in the sake of time, if we can actually maybe save all the questions towards the end, if that's okay. All right. So the next part here is to talk about parallel computation patterns. Hopefully these patterns are things you've maybe already seen in your workflow, but if not, we're going to cover them here. And so for the purpose of this talk, I want to have a working definition of what parallel computing means. So the idea is, just like you would be working with a group of people to get something done in a group, there's many threads and they need to work together to get some task done. And so what that means is threads read from the same memory location, threads write to the same memory location, and threads exchange information between each other. So let's start with the simplest of these patterns, which is the map. So the idea here is you've got many data elements, say a vector, an array of values, and what you'd like to do is you'd like to perform a function on each data element. So assume you've got a vector of like integers, and you want to like multiply each integer by 2. In a sequential solution, you'd have to iterate left to right, multiply by 2 every time, and do that sequentially. Well, on a GPU, there's a one-to-one correspondence between the input and the output, so you can do all 10 at once. So if I gave you 10 numbers in an array and asked you to multiply by 2, and each computation took 1 nanosecond, you'll end up having to wait 10 nanoseconds on a CPU. On a GPU, you just wait 1 nanosecond. You're taking the bus to Virginia. It's pretty powerful stuff, okay? Now, the map pattern could be easily expressed using CUDA threads, but because of its simplicity, it runs into trouble when you're trying to solve harder problems. So this next one I want to introduce you to, called the gather pattern, is very useful if you're trying to, say, compute a moving average and store it into memory, or blur a pixel image, given the neighboring elements around it. So yeah, so what the gather does in short is it basically looks at the input set as a neighboring set of pixels, and the output set is a reduced value from all those neighboring elements. And a stencil is a specific type of a gather, in which case you're using a fixed pattern. That fixed pattern is referred to as a convolutional kernel. So a lot of you who've done image recognition should be familiar with one-dimensional or two-dimensional convolution. And so we're applying this triad across the data set. So in this case, the 2D von Neumann is represented with a little plus sign, and the 2D more is a 3x3 grid. What I'm showing you at the top right-hand corner is the 2D von Neumann that's in blue, red, and yellow, and I'm just simply trying to show all three and how those reductions are happening. Okay, so this is very, very useful for obviously image, audio, and video processing. The next pattern we have is a scan, and so the scan operation takes a binary operator that's associative. In this case, let's just say it's addition, and it basically, and an array. And what it outputs is an array where each element j has the sum of all the previous values before it and j as well. That's called the inclusive scan. So back in the day, we used to balance checkbooks. How many people here have actually balanced checkbooks before? Okay, great. We've all now dated ourselves. Okay, so very simple. You basically take the balance, you take the credits, you take the debits, you add them up, and you've got a running total for today. This is what this is doing, okay? It's just doing the sum. And so but oftentimes it's useful to actually output an array where j represents the values before it, but excluding j, and that's called the exclusive scan. Okay, so that is a big deal because it's responsible for the fastest GPU sorting algorithms we have, but also a whole bunch of other really cool things like data compression, batch reversals, polynomial evaluation, which isn't up there but should be up there, etc. Okay? This next one here is really useful method for extraction notable features. So if you're doing image recognition, you want to look at feature extraction of important features, that would be useful, as well as if you're trying to monitor for fraud and given some credit card transactions. And the way this works is for each element in the data set, you basically use a value to identify a bin counter. So let's say I have 4 words, but if I have 4 threads and I point the threads at the beginning of each word, all I'm going to do is in parallel count how many letter groups I have. So in this case, you can see that I have 3 letters between M and P. This is also a big deal because it can help you deal with processing large data. And so the next one that I want to talk about is called a reduce, and the reduce uses a binary operator to take a commutative and associative operator, so that means the order of processing is not, the order that you process the data is not required, which means you're able to partition your input set into chunks and have each chunk basically be computed using a thread. And then what you do is you have this reduction tree that summarizes the partial sums. And you're not limited to just doing sum. You could do min, max, product, or sum. Let me show you an example of this because it's easier to do with an example. So what we're looking at here is thread 1, thread 2, and thread 3 are computing partial sums in parallel, and then thread 0 is doing that summary reduction. Pretty cool stuff. So you don't have to actually do this sequentially. Okay, so this is all great. We're working with threads, but we've got a problem. We've got a data race. Data races frequently occur if threads become interleaved. So in this case, we're starting out with 0, we're adding 1, and we're writing it out, except we have 2 threads doing that. And that's the code all the way in the top right-hand corner. So the first 2 scenarios are when things go right, okay? So thread 1 runs, after it completes, thread 2 runs, and we get a deterministic answer. We get the right answer. Scenario 2 is the same thing. Thread 2 runs first, then thread 1 runs, and we're good. Scenario 3 is when we have a problem. Thread 1 starts, as it actually reads the value, increments it by 1. Thread 2 now gets into the party, and it reads the old value. Then thread 1 updates the memory location, and then thread 2 clobbers it with the old data. Not a good idea. And scenario 4 is the same thing, except thread 2 is doing all. Thread 1 is the culprit. So there's a really easy way to obviously fix this, and you can use atomic operations, and CUDA has full support for it. As far as GPU programming languages, you're in luck, because if you're using C, C++, Fortran, you've got CUDA. If you're using MATLAB, then you're ready to go. I'm going to be showing you examples in obviously C++, Numba, and PyCUDA, for those of you who are interested in those. Okay, so Numba, is one of those libraries that basically gives you the power of all the stuff we talked about, parallel processing, data movement, etc., using Python decorators. So all you got to do is use the @JIT decorator is one of them. What that does is it basically says, hey, I want you to take the following code and create a kernel out of it. What a kernel means is it's a function that runs in parallel. That's what we mean by a kernel. And so in this case, basically the line 10 says, take that function and run it in parallel across as many workers and threads as you have. And I'll show you how to do kernel invocation a little bit. That's not a lot of work, and it handles all those details for you. The way Numba works is it compiles down to LLVM code, which is binary machine code. And so yeah, it works. It's portable across a variety of architectures, ARMs, x86s, GPUs, etc. Cool. So in CUDA, a kernel is executed by an array of threads. And so to recall, a kernel is just that function that's running in parallel. And so thread blocks are basically used to pull together runtime resources together. So what you're seeing here is basically there's 256 threads in each thread block. And thread blocks basically cooperate because they use the same shared memory. Threads in different thread blocks can't cooperate with one another. A thread can uniquely identify itself using the thread index, and a block can uniquely identify itself using a block index. And so this is really neat because if you're asking a whole bunch of threads to do work, they need to know who they are, they need to know where they are so they can perform the work in parallel. So that's kind of the big idea here. And the block dimension, which you don't see up here, actually you do, it's the number of threads per block, is normally defined by the hardware manufacturer when you purchase it, okay? So in this case, the block dimension is 256. One piece of info as well, CPU threads are a lot more heavyweight than GPU threads, so you don't really need to think about performance issues when you're talking about GPU threads. Here's the structure of a GPU program that I highlighted earlier. Just wanted to make sure there's a separate slide for it so you don't miss it. So yeah, the first step is to create the data on the CPU and allocate storage on the GPU. Next step is to copy it over from the host to the device. Then the next step is you can basically launch the kernel. The CPU launches the kernel, which tells the GPU to do all that heavy lifting work. And this last step is to basically copy the data back, the result back, from the GPU to the CPU. And those are all the functions that you could use in CUDA to help you do this. Now, I figured it would be good to have a demonstration of like a visualization of how the CUDA deals with kind of like this two-dimensional, two-level hierarchy, excuse me. So what I'm trying to show you here is that big brown or maroon rectangle or prism, three-dimensional rectangle is basically defining a grid. And within a grid, there's basically, sorry, kind of hard to see here. Yeah, so the grid is the brown or maroon stuff. The blocks are the lighter brown stuff. And the threads are actually, you know, the parts of that cube. And so what I want to point your attention to is each of those threads and blocks can actually be 1, 2, or 3-dimensional. So that brings us to the kernel invocation. So a kernel invocation is basically you telling your program and the hardware how much parallelism you want to have. So the first parameter into a kernel is the number of blocks. The second parameter is the number of threads. Those could be 1, 2, or 3-dimensional objects. And so in this case, for kernel B is showing that there's 64 threads that are going to be running whatever that function is that you're going to be doing. Kernel C shows that you're going to have basically a 3-dimensional block with the dimensions of 8, 4, and 2, and then you can have a 2-dimensional thread block for, 2-dimensional threads, okay? Okay, cool. So hopefully that visualization helps you out. Okay, so CUDA itself obviously ships with the MVCC compiler, which you can look at. What I want to show you here is basically the world's simplest program. It's a hello world in CUDA. So line 3 defines that double underscore global, that dunder global. That basically says that the code that follows in that function is going to be run in parallel. And then you can also pass system arguments, function arguments into it. And the rest of that is just regular C++ code. And so you can obviously use MVCC and look up the documentation to find out more. CUDA itself comes with a whole ecosystem of visual profilers, an integrated development environment, memory checker, etc. So, click on the resources if you want to learn more. And so here's a very simple vector addition. Basically, if you're doing things a sequential way, you're going to be using a loop to iterate left to right. If you're thinking about solving this using GPUs, you could do all the additions all at once because there's a one-to-one correspondence between input and output. And this is the parallel implementation using CUDA. Okay, and you can see how we use thread IDs and block IDs to identify each of the workers and what they're going to be needing to do. PyCUDA is an extension. PyCUDA is a wrapper for CUDA in Python, and it uses C extensions. So what it does is it basically can produce machine code that can run in parallel. Okay, and so I've got a snippet in the backup slides because I am running out of time. Part 3, let's talk about this. I mentioned OpenACC earlier, but I wanted to say a couple more words about it. So OpenACC is a directive-based programming model. That means you can sprinkle your code with a couple of directives and you're able to get the parallelism compiler. The downside is the performance is heavily based on the compiler you use. And the upside is it's easy to use. We're adding just a couple lines of code to what you already have, and you're basically getting the guarantee that it can run on several multi-core architectures. Alrighty, and this is, it's a little hard to see, so I'm going to go to this screen. But yeah, so what you're seeing here is basically on line 10, we're defining 32 workers to perform the kernels that we're going to be defining below. And line 14 and line 24 specify that the for loops for N and M should be running in parallel. And everything else does not run in parallel. So you could just put a directive right on top of the code and it will show you. It will know which one to run in parallel and versus sequential. And so, so yeah, in summary or in closing, what I want to do is I want to kind of reiterate how big of a deal this is. People are using GPU-designed databases now. People are using GPUs to visualize large data and big data. Obviously, the deep learning and AI use case is one you're very intimately familiar with. But if it all fails, you've got a great gaming machine. So yeah, I mean, I think I agree with him. It's a pretty cool box anyway. That's all I had. I want to make sure we have enough time for questions. There's actually 2 more slides. They're backup slides on PyCUDA if you're interested in seeing examples. And this is a discussion of basically MPI and OpenMP, but we don't have to get into it if you're not interested. How are we doing on time? Okay, cool. I do want to make sure that I'm respectful of the next presenter. So how about we take a couple questions? Or, by the way, if we don't have time because the next presenter needs to sit up, you're all going to come down here and we'll be happy to chat with you. Thank you for taking the opportunity to come in. Yeah, actually, just come on down.